So what I'm going to talk now is about the role of the EMI in this project. So our role is the development of hollow fiber membranes for CO2 capture in post-combustion processes. So EMI is, I don't know if you are aware, but there's a European Membrane Institute. It is located in Twente in the Netherlands. So our main aim is to be the bridge between academic research and industry. This is a very complex role, and but we have a very unique possibility to do that. So we are part of a cluster of the University of Twente. So the whole cluster is working in membranes, in the membrane topic, covering the whole range of applications: water, medical field, gas separation, organic solvent nanofiltration, everything you can imagine, and the whole range of size. So from really small size, so from Armstrong to really pilot scale, so square meters, so to the process design. So the aim of EMI Twente is to do the bridge between this knowledge that is generated in the cluster and the industry. So in order to cover all this gap that you can see on the field. So which is our main mission then is to valorize this academic know-how that is produced on the cluster and other places. Understand if this can be something that is suitable to be applied in industry. So at the end, what we do is we facilitate the adoption of this technology by increasing the knowledge and to understand if this technology may work. We also promote the membrane technology within the industry. So sometimes something is not applied just because the industry is not aware of the real potential of the technology. So at the end of the day, what we want to do, we want to be the leaders and providing services, but also unique solutions to the membrane industry. So we have a lot of capabilities. So the main capabilities we have is the development of membranes. So we have the possibility of develop hollow fiber membranes. We have multiple spinning lines. From small to large ones, and we can work under different environments, speeds, and control very well the conditions. We are also providing these spinning lines, so we are designing, and we have the possibility of selling them, also as well as the small pieces like spinnerets or part of the devices. We have the possibility of doing composite membranes, so by doing the coating process, multiple layers. We also have the possibility of doing flat sheet, although this is only in A4 size. This is not our main core, but we can do that. Of course, we have all the devices needed within the cluster to characterize the materials and the fibers we are forming, as well as the fiber properties, even the modules. So, to whom we normally work in the topics is different. So we cover the whole value chains. So it may be an industry that has a material that may have a potential to be applied as a membrane. So they ask to us to develop this material as a hollow fiber and then test it maybe. Or maybe a company that has already membrane or has already solution in place, but they don't have the possibility of characterizing, or they have some issues on the production, or they want to improve part of the process. It may be a technology provider, so there is someone that needs to know if this technology will work for something else, or they want to apply in a specific place, or maybe even the end user, so they want to know or they want to test it before they try in the processes. So we really cover the whole range, and we have quite a range of examples. So what is in terms of maybe European Union projects, what will be our approach is we cover the whole range from TRL2 to TRL6. So this means that we can do research, so we do feasibility studies. So maybe someone has to do wants us to do proof of concept. So they want to know if this something will work for them. We can also work in prototypes, so we not only stop in the proof of concept, so we go further and then we try to do it a little bit bigger and try to see if this works under real conditions. we can also go bigger. So we can do small pilot and then test in a pilot scale the membrane prototypes. As I mentioned before, for all kind of applications, from water to gas, but also medical factor, medical sector or solvent separation. So how can we do that is because we have different reasons. So we have very large experience. So this year we are working for 25 years on the topic. We have a really good team, a very big team as you can see here, but also very experienced. So we have more than 180 years of experience accumulated within the team. This allows us to collect a lot of expertise that allow us at the same time to work in multiple projects with, you can see here, more than 200 international clients and more than 500 projects. This bring us or provide to us really great experience in the topic that allow us to face any kind of problem that you can find on the process. So why these people is working with us? So normally because we always provide unique fundamental knowledge to them. So at the same time, they can access to our know-how and our expertise and facilities on the cluster. We have proven results, so we have worked with very big and important companies for a very long time, and we have provided results. So some of our products are in the market, and especially because we always provide a unique solution for the companies. So this solution is great only for them, and that's why we always give to them the ownership of the IP. So they always get the intellectual property of the research they contact with us. In practice, we have, as I mentioned before, several examples. Luckily, we cannot share all of them because confidential reasons, but this is one of them, one that we can share. So it's the case of Bonic. Bonic is a company that was producing polymers before. So at some point there was PSD developed in the MST cluster, so in the cluster of the University of Twente, based on the plasticization of polyimides or hollow fiber membranes. So this was an idea. So then they understood that it may be interesting for them. So they went from the material, they had the material, they went from the material to the proof of principles. So they developed fibers, and they tried to understand if this would work for their specific application. So after that, they took over. This is what we did at EMI. They took over and they commercialized the materials. So in a very fast time, very short time, in less than 5 years, they were already in production. So they were commercializing this in a really big scale. This is a clear example of success for an industrial partner, but we also work in European projects. So this is one of the examples. So here we were doing hollow fibers for the hydration of flue gas. And, again, so we cover from research to the pilot. So which is our role here in the Genesis project is more or less the same. We have to cover the whole range from research to testing. So we do one part. So we do the feasibility study. So we prove the principle, and then other partners will take over doing the production, the prototype, and of course the process design and testing in place. So you will hear about that later. Not gonna talk about the process itself. I think Marcel did already. Very good. So I'm gonna talk here only about the process conditions. So what we need to pay attention is to the process is that we have a very low CO2 concentration, 5 to 15%, very low feed pressures, or very low pressures, something around 1 bar. The temperature of the process is between 40 and 60. It depends on the process design. And we have also the presence of different contaminants on the gas mixture, as you can see here. So what that means is when we pay attention to the combustion process, and we check the basic things, so the transport model, what that really means is that we have a flux which is highly limited for this driving force. So driving force is the difference in pressures. I told you there's very low concentration of CO2 and very low pressure. So we have a real limitation on the driving force. Because we have this limitation in order to have high flux, because we are getting a lot of volume of gas to be treated, we need really highly permeable materials. So how the properties of the material should be. So then we need to understand which is the selectivity we need, and attending to that, we will also find out what. So if we attend to the selectivity, we understand that there is a huge limitation on the pressure ratio. Again, so low feed pressure, low concentration of CO2. So even if we have very high selectivity on the material, this selectivity will not be effective. Selectivity will be always so the pressure ratio will always limit the selectivity. Therefore, the optimal selectivity we need to find for the material for this application is something between 30 and 50 CO2 nitrogen. And the higher is the CO2 permeance, the lower will be the membrane area, which will mean the lower will be the cost. So how we select the material is we have this typical Robson upper bounds where we can draw here the optimal selectivity range, as I just mentioned before. And if we check that and then we go to the highest material, highest permeable material we can find, you can see this blue circle here, which all of them are belong to rubbery polymers. Rubbery means that at room temperature, or at least the temperature of the process, this material is soft. So the TG is lower than the temperature of the process. Because the material is soft, it means that it has to be supported to provide some mechanical stability. According to this strategy, this is what we designed for the Genesis project. So we have a multi-layer approach where we have a porous support, then a gutter layer, and then our selective layer based on the rubbery polymer and combination with the MOFs. Jose just described good properties of these materials, and the separation and capture of CO2. Then at the end, we have a protective layer that makes everything more stable. At the end of the day, what we need is an overall membrane performance, which is defined as you can see here. So CO2 permeance higher than 2000 GPUs, and selectivity is something around 50. So practically how this looks like is we first, told you before, we are doing our main core is hollow fiber. So we do hollow fiber as a porous support. So we do the spinning of the porous support. Then we cover this with an extra layer, the gutter layer. Then we place the selective layer and then the protective layer. As you can imagine, this has a different limitation, viscosities, concentration, speeds. So this is quite complex, and it has to be optimized in order to get the thinnest layer and highest material possible. So at the end, what we develop is we have a concept that was developed in very small scale, and then we have to bring it to kilometers because we have to place it on the site. So we have to make models after that. So the first we do is with the spinning line, we can develop kilometers of these porous supports. It's quite fast and quite big, and we have the capabilities for that. After we have this porous support, we can do the coating of the different layers. And of course, between the process and during the process, we have to characterize what is the quality of the material and if we reach the performance we want. At the end, what we have is fiber that will looks like that. So we have the 4 layers we mentioned before. And yeah, this material will be developed by different partners, and then at the end will be tested on site. I think you will listen later the process design and how this will be placed on the site. With that, I would like to thank you for your attention. Thank you for the invitation, and I will be happy to answer any question you have